Hey everybody, welcome to video 12-3. In this video, we're going to be talking about how to use the ideas of similarity that we've encountered in Module 11 to figure out some application problems to the real world. So talking about how to measure distances that maybe we are unable to measure directly, and if we are having any barriers to physical measurement of whatever it is we're looking for, then we can use the idea of what we call indirect measurement. And so indirect measurement involves using the properties of similar triangles to measure such heights or distances that are hard to measure by hand. Okay, so in part A, we are thinking about a scenario like we see in the picture over here, where we have a flagpole, and if we want to know how tall the flagpole is, but obviously it's hard to climb to the top of the flagpole and measure that, what we can do is use similar triangles to get there. So let's do the walkthrough here for this explore. It says, during the day, sunlight creates shadows as shown in the figure below. The dashed segment represents the ray of sunlight. What kind of triangle is formed by the flagpole, its shadow, and the ray of sunlight? And I hope you guys can see, assuming that this flagpole has been, put into the ground correctly, that is a right triangle. So in part B, if we're supposing that the sun is shining and that we ourselves are standing near a flagpole, but outside of the flagpole's shadow, so that we can see kind of two shadows on the ground here and here, what we want to do is use the idea of similar triangles. Well, if we're going to use similar triangles, we know that we have three shortcuts that will work for us to be able to assume that the triangles are similar. That's side, 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 angle, side, or angle, angle. So let's see which one applies here. Do we know all three pairs of sides? No, we don't know those. Do we know two sides and the angle in between? Well, you might think we might know SAS to prove that these are going to be similar. Clearly we can measure a shadow along the ground, so we're able to see that shadow of ourselves. We know how tall we ourselves are, and we can see the shadow of the flagpole, but because this one is still in question, we can't use side angle side either. So what we need to be able to do is to use the idea of angle-angle similarity. And the reason that we can do that is from what it says in the problem here. We can assume that our rays of the sun are parallel, you guys. And so if these dotted lines, which are the sun's rays, are parallel, then any angles formed by parallel lines and transversals we can assume are going to be congruent. So we can mark this angle right here as congruent, and then as soon as we do that, then we've got angle-angle similarity. So now let's use that in the next couple examples. So in Explain 1, Example 1, Part A, it says find the indicated dimension using the measurements shown in the figure and the properties of similar triangles. So in order for us to know how tall this palm tree is, we are going to measure the shadow along the ground of the tree, and the same time of day we're measuring the shadow cast by a 1 meter tall stick that we're holding at the same right angle to the ground as we can assume that the palm tree is. Okay, so we've got our right angles here and here. What we want to find is the height h of the tree, so let's label that h, and let's go through and set up why we can say they're similar. Again, remember, is angle-angle similarity. So now we're going to set up a proportion. For AB over XY, we can see that our numerators are going to come from our right-hand triangle, and our denominators are coming from the left. And the left-hand ratio, if we do AB to XY, those are the actual heights, and the right-hand ratio are the shadows. At this point, you guys, we need to modify what's in your book. I'm not sure if your proportion is written correctly or not, but what I have in front of me is not consistent with what they just told me to walk through as far as a proportion goes. As you can see, the length should be h over xy's length is 1 is going to equal BC's length, which is 7.2, divided by YZ's length, which is your 1.6 meters. And so if we do that math out, it's very easily able to get us to 4.5. You don't need to worry about this middle step here if you set up the proportion correctly, and notice that the denominator being 1 does simplify our math quite considerably. So the tree is 4.5 meters high. And notice as we answer, we want to make sure we put in the units. All right, let's look at our next example. Part B, we are again going back to our example of a flagpole that we had in our Explorer. And it looks like we are measuring our height in inches. So Sid is 72 inches tall, it says here. To measure a flagpole, he stands near it, and his friend Miranda measures the lengths of the shadow of Sid and of the flagpole, and what we need to figure out is find the height of the flagpole. We know that triangles are similar by angle-angle similarity because of that idea that our angles of the sun's rays are always going to be congruent to each other. So if we set up a proportion, we are going to put what we want to find in the numerator, because that makes sense. So the flagpole's height to the person's height, and then we want to go from flagpole's shadow to person's shadow. There are measurements that we know and measurements that we don't. The one that we don't we'll keep in the numerator. So height to height will be h to 72 is going to equal shadow to shadow, which is 128 over 48. And let's do a little bit of LCD work here, because we can clear out our denominators by finding the correct LCD. So for the LCD of 72 first, we know, you guys, that that is 8 times 9. 8 is also the third power of 2, and 9 is the second power of 3. Our other denominator is 48. This one's a little trickier. We know that it's 12 times 4 is 48. 4 is actually 2 squared itself, and so we have another 2 squared times 3, or 4 times 3, that gives us 12. Altogether, that is actually 2 to the 4th power times 3. So when we merge to get an LCD there, we know we have a factor of 2, we know we have a factor of 3, but the highest power that is used in any one factorization is that we go all the way up to the 4th power of 2 and the second power of 3. In other words, 16 times 9, or our LCD, is 144. Sorry, stylus issues there. 144. So if I multiply both sides by that LCD, what's going to happen is that we're going to cancel out with common factors in the denominators. This is going to leave me a 2, and this is going to leave me a 3. So I have h equals, I'm just going to go off to the side here and do my own thing, because it's 2 as a factor that is left over, times h, or 2h, is going to equal 128 times 3 times 3. And so 2h equals 384 when we do that multiplication, and a division is that h, not x, h comes out to be, by 2, h is 192 and so that's 192 inches tall. Now keep in mind that that might make more sense if we actually convert it to feet. So convert by dividing by 12, and we get 16 feet tall is how tall that flagpole is. So that's what we're going to be encountering, this type of problem, as we do indirect measurement. Okay, on the next page, your turn, number 3, with that same idea of finding those unknown heights. Okay. Alright, now we're going to be finding unknown distances, not just heights. So we have sometimes, just like we can't climb the flagpole or climb the palm tree to do the measurement, sometimes it's hard to be able to measure something because there's some sort of physical barrier that is separating you from the object, as it says here in Explain 2. We can still use similar triangles in these situations if we set it up just right. So in example 2, it says explain how to use the information in the figure to find the indicated distance. It says a hiker wants to find the distance d across a canyon. Okay, so we are looking for this value here. It says she locates some points as described. It says she identifies a landmark at X, and she places a marker Y that is directly across the canyon from X. Then at Y, she turns and walks 90 degrees away from X and walks 400 feet in a straight line and places another marker at that location, which is Z. Then she marks another 600 feet past that and continues walking, places a marker at W, and then basically turns and walks another distance until she can see the spot on the canyon align with the marker at Z, so that we have a straight line coming across for a line of sight here, and that distance she measures at 327 feet. Alright, so why are we able to say that these are similar triangles? Well, we've got two right angles at first, and because we've got a line of sight that crosses right through the side of the canyon, that is going to create for us some congruent vertical angles. So we have angle similarity working in our favor here, and to find the missing distance, we just need to set up a proportion. So our proportion is xy to vw, the vertical distances, is going to equal yz to wz, or the horizontal distances. So that is going to be d over 327 equals 400 over 600, or of course make sure that you know that that can be simplified down to 2/3. It's going to make my life a whole lot simpler when I do that. And our LCD in this case, pulling that off to the side really quickly, LCD is between 3, which has no other prime factorization other than just 3, and 327, which has factors of 3 times the prime number 109. And when we merge those two prime numbers together into one LCD, prime factorizations into one LCD, we're going to use both factors that are there. So 3 times 109, or back to 327, is actually my LCD. So one of the denominators is my LCD. When I multiply both sides by that LCD, we see that the 327s on the left completely are canceling out because all common factors are going to go away. And then this 3 is going to leave a factor of 109 left over in the numerator. And so we have that D equals 218 when all is said and done there. Moving on to our next page. This is page 656. I've got one more example and then a your turn, you guys, to do here. Still using the idea of similar triangles. To find the distance d across a gorge, a student identifies some points and marks them just like we talked about. So identifies a point directly across, walks along the path on a straight line, and then turns basically. So walks and marks, and then turns until we see all of these two markers in one line of sight here, and puts another marker. So we know we have vertical angles that are congruent, so we have angle-angle similarity, and let's just set up our proportion. So d to 35 vertical components is going to equal 24, because we want to keep with that left-hand triangle's measurements in the numerator, and the right-hand triangle's measurements in the denominator will be 24 over 42. If I look off to the side here with a quick LCD analysis, 35 factors to 5 times 7, and 42 is 6 times 7, or 6 is 2 times 3 itself, times 7. This is a great example of an LCD problem because we have to remember take all factors that are present, so 2, 3, 5, and 7, and we have to take them to the highest power that any of them are used individually. And it looks like all of these are to the first power, so all I need to do is just do a product of these 4 factors, 4 prime factors, and we have 2 times 5 gives us 10, and 3 times 7 gives us 21, so this is 21 times 10, or 210 is our LCD. I'm not going to go with the work that you see really on your layout of your textbook, because we want to use this idea of LCD consistently. So there's our 210 multiplied on both sides. 42 is going to divide into that and leave me with a factor of 5. And 35 is going to divide into that and leave me with a factor of 6. So let's go over here, you guys. This is going to be 6 times the distance d that we need to know is going to equal 24 times 5. And that simplifies down to 120. And so my distance is 20. And of course we're doing units, so this is in meters in this case. All right, your turn, guys. Number 5, check in on that problem with some indirect measurement, and we will see you guys in class tomorrow.